chemical reactions and equations, balanced chemical equation. So today our topic is balanced chemical equations. If you recall the concept of balanced and unbalanced or skeletal chemical reaction, you might have already realized the importance of balancing a chemical equation. We balance it to follow the law of conservation of mass, which we have already discussed in early sessions. So now let's talk about how to identify any balanced or unbalanced equation, and if it is unbalanced, how to balance them. Let's consider this example: zinc plus sulfuric acid forming zinc sulfate plus hydrogen. As we all know, it's quite convenient to write any chemical equation in its symbolic form. So here's the symbolic form, which is Zn plus H2SO4 forming ZnSO4 plus H2. Now, to identify whether the given reaction is balanced or unbalanced, let's count the number of atoms of each element on each side and tabulate them in this form. So we have 4 elements in total in this example. In the left hand side of the arrow, we have 1 zinc atom, and in the right hand side, it's 1 as well. Similarly, if you count the number of atoms of each element on each side, you will observe that the number of atoms of each element is equal on both the sides. Now, if you recall the previous session, you will understand that this is a balanced chemical equation. So it was quite easy because you know that number of atoms of each element on each side is equal, right? So identifying a balanced chemical equation is really simple. Now let's consider this example: Fe plus H2O forming Fe3O4 plus H2. Here we can easily say that this is an unbalanced equation just by counting the number of atoms of first element on each side, that is Fe. So now to balance it, we will have to follow some specific steps. The steps to be followed: step 1. Draw boxes around each formula. Remember not to change anything inside the boxes while balancing the equation. This is quite important because while balancing the equation, we cannot manipulate the content inside the box. So I have drawn the boxes around each formula. And remember that we can only multiply or divide the coefficients of these compounds or these formulas. Now step 2 is to tabulate the number of atoms of each element on each side present in the unbalanced equation. So I have tabulated this data again. We have 1 Fe atom in the left hand side and it's 3 on the right hand side. Similarly, we have 2 hydrogen atoms on both left hand side as well as right hand side, and so on. Remember, even if one element in the equation is unequal, whole equation gets unbalanced. Now step 3. It is not a compulsory rule, but one should usually start balancing the compound that contains maximum number of atoms, be it a reactant or a product. Accordingly, we select Fe3O4 and oxygen atom within it. Now the table displayed here counts the number of atoms of oxygen on left hand side and right hand side of the equation. The first row shows initial number of atoms. We have 1 oxygen atom on the reactant side while there are 4 on the product side. So to balance the number of atoms, we multiply the coefficient of H2O on the reactant side with 4. Now how to write this 4? Should we write it in coefficient form or in subscript form? Let's understand. It is important to remember that we cannot alter the formula of compounds or elements involved in the reactions. So we cannot manipulate anything inside the box, right? For example, we can write 4H2O but not H2O4. Remember, while balancing the equation, we can only perform multiplication and division of coefficients and not addition and subtraction. So after this step, our partly balanced equation looks like this. We have multiplied the coefficient of H2O by 4. Now, here we can see that Fe and H are still unbalanced and we can consider any of them and proceed further. Okay, so either Fe or H, we can consider any. Now, another point to note here is that H or hydrogen was initially balanced, right? See in step 1, it was 2 on both the sides. But after multiplying the coefficient of H2O by 4 for balancing these oxygen atom, we are actually disturbing the balancing of hydrogen. And so always remember that we have to consider the updated equation, right? We cannot now, after step 3, we have to consider the equation which we got at the end of step 3, right? So let's go further. Step 4, let's consider the atom of hydrogen first. Okay, like we did for iron in the last step, we have tabulated this data. We have tabulated the number of atoms of hydrogen on both the sides. So here we have 8 hydrogen atoms. How 8? It's 4 into 2 equal to 8 in the reactant side, while it is only 2 on the product. Now how will you convert this 2 to 8? Yes, 2 into 4 is 8, right? So we will multiply the coefficient of H2 on the product side by 4. So 4 into 2 becomes 8, and so number of hydrogen atoms will become 8 on both the sides. You can observe here in this partly balanced equation that we have multiplied the coefficient of H2 or hydrogen by 4. Now observe the atoms again. Go from left to right. The first atom is Fe, right, which is iron. It's 1 on left hand side and 3 on right hand side. Next is hydrogen, which is 8 on both the sides, and oxygen, which is 4 on both the sides. So by this we can conclude that we have only Fe or iron which is left unbalanced, while all other are already balanced. Now step 5. Examine the equation and consider the one which is still left unbalanced, and we have already examined it. So yes, you are absolutely right. Fe is left to be balanced, and so let's tabulate the number of Fe atoms on both the sides. Here to balance Fe atoms, we need to multiply the coefficient of the reactant side Fe and the reactant side by 3. Okay, so if you see the equation, we have multiplied the coefficient of Fe or iron by 3. Because it was the Fe atom initially was 1 in the reactant side and 3 on the product side. So to balance, we have done this. Now the equation looks something like this, right? We have mentioned here that it's a balanced equation. It's not, because even if we are done with the balancing, but number of atoms of every element should be equal on both the sides for becoming balanced. Now we have to cross check this equation again, like we have to check it again, and so we will perform this step 6, which is finally to count the number of atoms of each element on each side. Okay, so after step 6, we can say that we are finally done with the balancing of equation. So the final balanced equation is 3Fe plus 4H2O forming Fe3O4 plus 4H2. But wait, there's still something missing, right? Can you guess what it is? Yes, step 7 explains it. So to write the physical states, okay, we have to involve the physical symbols. To make a chemical equation more informative, the physical states of the reactants and products are mentioned along with the chemical formula. We have to mention these two for our information and to make this equation more informative. Okay, the gaseous, liquid and aqueous and solid states of the reactants and products are represented by notations G, L, AQ and S respectively. The word or aqueous or the symbol AQ is written if the reactant or product is present as a solution in water. So now here you can say that gaseous can be symbolized as G inside the bracket or small g. Liquid can be said as small l inside the bracket, aqueous as AQ and solid as S. Now let's write the balanced equation along with its physical state. The symbol G is used with H2O to indicate that in this reaction water is used in the form of steam. Okay, so in some condition it might happen that H2O is used as a steam. Okay, so to symbolize this we use H2O, and after writing H2O we write this G in brackets to indicate that it was used in the form of steam. This method of balancing chemical equation is called a Hittan trial method, as we make trials to balance the equation by using the smallest whole number coefficient, right? We are actually trying it, and it's not just You can't define any method to actually balance it. You have to use this hit and trial method, and this is how we actually perform it. Okay, so now in step 7 or the end of step 7, we can see this equation 3Fe, which is in solid state, plus 4H2O, which is in gaseous state, forming Fe3O4, which is in solid state, and 4H2O, which is in gaseous state. Okay, so these gaseous, solid are actually giving us information about a compound formed, right? About the reactants and the products. Sometimes the reaction conditions such as temperature, pressure, catalyst, etc. for the reaction are indicated above or below the arrow of the equation. For example, we can take it like this. Like in the displayed picture, we have mentioned the pressure condition to be 340 atmosphere for optimum result of the reaction. Similarly, see the second equation, it's 6CO2 plus 12H2O. Again, we have this two words written, sunlight and chlorophyll, above and below the arrow. What it says is it needs sunlight and chlorophyll as it needs it for the reaction to happen. Okay, so you can say that this reaction happen in presence of sunlight and it needs chlorophyll to perform this reaction. So now we are done with balancing equations, and meet you in the next module. Thank you.